In this demo, you will learn how to submit a job or a model run on the cluster. So we're already logged in onto the cluster, and in the previous demo we just learned how to compile the code in the source directory. So of course the first step was to go inside applications here and compile the example Coriolis here, which I'm going to do now. And so let's finish the compilation first to make sure that it produces a binary file. And after that is complete, we're going to go and try to submit our first run. Now on cluster machines, as this finishes compiling, typically you need to submit the run into a queuing system, meaning you don't directly run the job, the ROMs model from the console like you would type any other command like the ls command. But you have to just prepare a script and send it to a queuing system, and the queuing system will execute the script following a certain priority list so that multi-users can submit jobs at the same time, and the queuing system can keep track of this. So for example, in this case the executable has been placed in this directory here, which is ROMs example Coriolis bin, etc., etc. And in fact we can look whether the executable is there, as we said before, and in fact it is there. And now we're going to go in this ROMs example directory that I prepared for you as a beginning, as an example of executing ROMs on the cluster. And you can access this directly from your home directory. It's right here, ROMs examples, and we go inside Coriolis. Okay. Now the way that I prepared this directory, first let me clean some stuff that is left over from a previous run so that we can start from scratch. So in this script, in this directory, you find many subdirectories. There's a directory called bin, which contains the executable. There's a directory called input, which contains some input files that you need to provide ROMs at running time. And then there's a directory MATLib that contains some programs, MATLAB programs that I'll use to plot the solution once the script is done. And then there's a directory scripts where I keep some junk in case I need it. And the most important script here, though, there's a file here called run model PBS, and this is a script file that you use to submit the model on the cluster. Before even looking at the script, the way you would submit the script is to just type qsub, which is the command used to submit a job to the queuing system. You type this and then you just press return. Once you've done that, you can check whether your model is running by typing qstat, and you can see that in fact you have a job ID for this run, which is 6499. It says that the name is ROM, so your user is root. And then the other important thing here is the status, that is this column here which says running or is running. Sometimes if there's other jobs that have been submitted, you may have to be waiting for the jobs to be executed and so forth. I can always interrupt this job if I want by typing qdel and then putting the job ID. And if I did that, this will basically kill your job, and so you could start it over again. But for the time being, we'll just let the job run, and so I'm not going to kill it. And I'm going to type an ls. And when you submit the script, you have a log file here that is generated where you have information about the output of the log of the model. And if you look at this, you find that that there is in fact this job has been executed on 4 nodes, on 4 CPUs. All these CPUs are on node 33. In fact, on this cluster, each node has 4 CPUs. And you can actually, at any given time, you can check the status of the various CPUs on the cluster by entering the command clstat. I'm going to do it now. And this command lists all the nodes of the cluster. And while it lists all the node, you can see here whether there's any kind of job running. In this case, you see the CPU is all 0, so there's nothing running right now because I have closed the cluster for this training. And once we get down to CPU number 33, of course there's nothing running because the model has already finished running. if we do qstat, but let's resubmit the job, for example, so we can run model. And if now we type clstat, the job is running. We have to go through the whole node list, but you will see that when we reach node 33, there's going to be the job running, and you can find the ROMs in the background. Okay, almost there. And there you go. And so, for example, here you see your Coriolis ROMs is running, and it's using there's four processes of this job here, each one for each CPU, and it's using 99% of the CPU, which is very good. We're basically using all the computational power. So that's very good. So having said that, which is just the basic, now how does this script work? Well, let's open this run model PBS, and let's describe a little bit what we find in the script. The beginning of this is a simple shell script. These first groups of lines are actually comments in a typical shell, but these comments contain some information that the queuing system wants to know. For example, PBS, this # PBS is an instruction for the queuing system. -n means that the name of the job is going to be ROMs. This is just a simple comment line. PBS -r equals n is a switch that you don't care about right now. Then there's a switch -e, PBS -e, and then the name of a file that it's going to contain errors, meaning that if the queuing system encounters errors in running your job, it's going to give you some feedback inside this file here at the end of the run. And there's also going to be a file that is called pbs.log, which is just a simple log file of the queuing system. It's not the log file of the model itself per se. Then you have this string here, which is important. It says PBS -L, and this is where you specify the number of CPUs that you want to use. To specify the CPUs, you have to give two information. First, the number of nodes that you want to use, and you have to keep in mind that different cluster may have nodes that have 1, 2, or 4 CPUs. In our case, our cluster has 4 CPUs, so in order to run this code on using 4 CPUs, we're going to say that we're going to use 1 node and 4 CPUs on that particular node that we're going to use. And this allocates basically your computer time on the cluster. Alternatively, you could have said, well, I want to use 2 nodes, and on each node I'm going to use 2 CPUs, and this also it would be equivalent of using 4 CPUs. But for the time being and for efficiency, on this cluster we'll always try to use 4 CPUs on each node. Now, following that, there's some variables that you define here for your run. The first one is the directory where this example is contained. Okay. Then you're going to define a variable log file, which contains the name of the log file where you're going to store the information relative to the model run. And you can see that this log file is defined by using this dynamic variable directory, which is the directory where this example is, which you have just defined up here, and then /log. You also want to tell it, initialize the variable bin, which contains the executable, and then the variable input, which contains the input file for the model. Now, this input file coriolis.in, which is inside this the input file. Let's actually look at it. Inside input, it's right here. Let's do an ls so you can convince yourself that it's here. This thing is a file that is used by the model to provide some standard runtime parameters. These parameters are essentially parameters that you don't hardwire in the Fortran source code, and that's because you may want to change them often to run various cases. Parameters in these files that are important, for example, are n times, which is the number of time steps that you want to run the model for, dt, which is, for example, the time, the times in second of the time step. So this is the time step would be 200 seconds, and other stuff. Important parameters that you want to keep track of are characterized in this particular file by the string edit. So if you look for the string edit, you will be brought to, you can search this in the file, and you'll find all places where you always want to check before you run. There's first occurrence here is ntile I, which is which is the domain decomposition. So we're running in parallel. So in this case, we want to use 4 CPUs. So we want to decompose our computational grid in 4 quadrants. They're also called tiles. And so in this case, I divided the I direction, which is the X direction, in 2, and the J direction in 2, so that I have 4 quadrant, as I said. Then there's this other edit occurrence, which is the time stepping. Let's go to the next one. In this occurrence here, one parameter that you want to keep in mind is this nhis, which is how many times, after how many time steps do you want to save a snapshot of the model solutions. Okay, so in this case, nhis is equal 18, and the time step is 200 seconds. So if you multiply 200 seconds by 18, you get a total of about an hour. So the model is saving an output every hour, and because this is a case for the initial oscillations, it makes sense. And so that's very good. So we can go further down and find other parameters here that you can eventually read what they are. And these are, coefficients for the bottom jack coefficients. And here are, for example, other parameters like the names of the files where you want to save the model solution, and so forth. Now, all these variables, if you don't know what they are, these parameters, you can go towards the end of the file. And there's a glossary here which explains in great detail the meaning of each of these parameters. You see n tile I, n tile j, n times, dt, and you can read this. So actually a good thing to do would be to print this file and have it so that you can keep an eye on it when you want to configure your input parameters. Keep in mind that not all these parameters are used at all times, but just the ones that are needed for the current application. So a lot of these parameters, for example, if we go further down, here you have parameters. These are mixing coefficient for the horizontal. This is TNU2 is for the temperature for the tracer's equation. And these mixing coefficients are constant and are used if you use, for example, by a Laplacian type mixing, which is a del square type mixing. And this is TNU4 is for del square mixing, a biharmonic mixing. Now, of course, you typically just choose one of them. So depending on which one you selected, the input parameters will be read only for the one that you are currently running. So you'll have to learn with some experience how to use these input files, and typically what you do, you just copy an existing one and you modify it. So that's a short digression. So let's go back to our run model PBS. And so as I said, after you provide here, we provide the directory where the example is, the log file, the binary file, and the input file. All the rest here is just stuff that you don't have to modify on the cluster. And but I'll tell you exactly what it is, just to give you some sense of how these things work. Here we now define a new variable called PBS_O workdir, which is a local variable that the queuing system needs, which is he needs to know where the local directory is. Then it has a dynamic variable that we did not initialize, but it's initialized by the queuing system. It's called PBS node file, and this is basically the list of all the available CPUs on the cluster. And so it wants to know how many processors you have, and so it does that by just doing this particular command WC, which basically counts the number of CPUs. Then the first thing it does, it changes when the script executes itself through the queuing system. It goes in the PBS working directory, which is your directory containing the example. Then it does a whole bunch of little diagnostic. For example, it's this echo in the Unix shell just means that it just displays this string here. So it says time is, and then it computes the date and it puts it into the log file. So it tells you, when the job started. Then it tells you here, this job runs on the following processors, and then it cuts the PBS node file, basically lists the names of the CPUs, and it puts them into the log file so you can see on which CPUs the system is executing your job, and then some other stuff. The most important command is down here, and this is a string of the so-called MPI run command, which stops right here, the string here, and this is the command that is used to submit an MPI, a parallel job on the cluster. Now in principle you could run this job interactively by just running this whole command here. but of course you're not advised to do that because otherwise you may be different users may be concurrently running jobs at the same time, and so you don't know which nodes are available for you to run, and you may just it may not be very efficient. You may be competing with other people for the same CPU. That's why we have this queuing system. Now the MPI run command, in this case, because we're using the Intel compiler, it has the Intel here, and otherwise if you were using, for example, the PGI compiler on this particular system, you have to locate the location of the MPI run for the PGI compiler, and in this case, in this particular system, it would be just PGI. Okay. Now the MPI run command in MPI run infrastructure is typically already present on the cluster, so it's not something that you have to provide yourself. So the input arguments for this command are -np, and then there's this dynamic variable nproc, which is the number of processors which the queuing system has defined. Where is it? Nproc right here. Okay, so this is where it knew which processor numbers. So this is the number of processors. Then minus machine file. This tells us where the processors are located, on what is the name of the node that contains those CPUs, and this is contained in this PBS node file directory. Then you provide the binary file. You do it through this dynamic variable which you initialized over here. The input file, which in this case is this Coriolis.in, and then you redirect all the output of the model execution into a log file, which is what you defined over here. So with this in mind, then you are good to go. Okay. Now to give you an example, I said that you in principle could run this interactively, and I just want to give you an example that this works, but I would never want you to do this. So if we cut this script, okay, so what you need to know here, the input parameters are the number of processors, the machine file, the executable, and so forth. So for example, the first thing you would need to create is a file that contains the name of the nodes, or where you have available CPU. So I'm going to create, for example, just for the heck of it, a file called nodes.txt. Okay, and I'm going to put here the name of some nodes, node 33, for example, node 32, node 31, node 30. So now I have 4 computer names, 4 nodes names that contain a CPU available. I save this. Okay, and then the next thing that I do is I can try and run this job interactively. Okay, but you're not going to do this. -np, the number of processors that I want to use in this case is -np4. Then I'm going to say minus machine file equals nodes.txt. Then I have to give the binary file, which in this case is contained in this directory. Okay, in this case you want to give the full path. Okay, so I'm going to put this full path. Then I have the name of the binary file, which is Coriolis this. Okay, and then I would have to give the name of the input file, which I'm just going to assemble by taking the full path again. Okay, you see it's starting to be very long, but this is the way it works. Okay, and so now I could redirect the output into some log file, but because I'm running on the screen here, I want to see the model showing me some stuff as it runs. So I'm just going to execute this, and you can see that in fact the model is running, and now you're running interactively. And once again, if you now go on another window and you type the command clstat, you'll find that eventually when this comes to node 33, it'll show the ROMs running. Let's see if it's still running. Yeah, you see, so this is running interactively right now. Like, once again, never do that, please. But this is just to show you that if you have to do a quick debugging, perhaps this could be, you could run it, like this for once. So you can see now that in this case I selected, node 30, 31, 32, and 33, and so in fact now the processes are distributed. One process is on node 30, another one on node 31, another one 32, and so forth. Whether before we were just using only the 4 CPUs of the node 33. Okay, so in this case we just rearranged the workload in a different way. Okay, so I'm going to stop this, and if you really find yourself in the need of running an interactive job, Okay, just to if you were having some errors, for example, you need to debug. If you go in the directory scripts, okay, there is a little script example here called Run Model Interactive, which provides you with you know, with an example of a script that you could use to run interactively, you know, the job without having to put all the things. And in this case, you define the PBS workdir here, the PBS node file, which is just the scripts nodes.txt and so forth, and then you have a working dir and so forth, and then you just run this. And you can look through this and you can understand it yourself if you want to run interactively. Okay, so so this really ends our example here. And one last thing, you find that at the end of when you submit this job through the queuing system, at the end you will find these log files of the queuing system that are called PBS log and PBS error. And in general, if the execution has been completed without problems, the PBS error file will be 0, and the PBS log will just contain some very basic logging information of the queuing system. Okay, so this is all for the running jobs, submitting jobs on the cluster.